Understanding the performance of complex software systems has always been like trying to diagnose a car engine while driving it blindfolded. For years, we relied on static metrics and logs to tell us when something was wrong. We knew the speed was low, but we rarely knew exactly why the engine was sputtering. This is where the recent announcement regarding OpenTelemetry Profiles changes the landscape. The project has officially entered its public alpha phase, marking a significant shift from observing what happened to understanding how the machine actually executed the work. This is not just another update to a dashboard, it is a fundamental change in how we capture and analyze the behavior of our applications at a granular level. Consider the specific challenge of optimizing data pipeline efficiency in machine learning environments. When you run an inference request through a model, the time it takes to return a result is often dominated by CPU-bound processes. In traditional setups, you might see a spike in latency and know that the system is slow, but you cannot distinguish between a network delay, a database lock, or a central processing unit bottleneck. OpenTelemetry Profiles changes this by enabling continuous, low-overhead collection of profiled data. This data captures the exact sequence of instructions the processor is executing, along with memory usage and call stacks. This allows us to correlate high-level request latency with specific kernel traces. To understand the power of this, imagine you are listening to a symphony orchestra. Traditional monitoring tells you that the music is too quiet. It gives you a volume meter. But profiling tells you that the violin section is playing out of tune because the conductor is moving too slowly. By capturing the execution traces, we can pinpoint exactly which line of code is consuming the most cycles. In the context of machine learning inference, this means we can see if the latency is caused by the model computation itself, or if the operating system is struggling to schedule the tasks correctly. We are moving from a system that tells us when it is slow to a system that explains the mechanics of that slowness. This capability is particularly critical for data pipelines where efficiency dictates cost and user experience. If a single inference takes 10 milliseconds instead of 5, and you are processing millions of requests a day, the difference is massive. With the new profiling standard, we can correlate this CPU-bound latency with kernel traces. Kernel traces are the records of how the operating system manages resources like memory and processor time. When we combine these two data streams, we can see if the application is waiting on the hardware or if the hardware is waiting on the application. This correlation is the key to optimizing the pipeline. It moves us from guessing to knowing. However, it is important to acknowledge the current state of this technology. While the public alpha launch signals a strategic pivot where traditional application performance management vendors and cloud providers are racing to standardize on a unified format, the ecosystem currently faces rough edges. The community consensus indicates that the tool is an evolving platform rather than a finalized product. For instance, there is a lack of native exception capturing comparable to specialized tools like Sentry. This forces users to rely on third-party integrations to get a complete picture of errors. Furthermore, recent changes to metric naming conventions have caused disruptions in existing dashboards. Teams that have spent years building monitoring views may find that their historical data is now harder to query without adjustment. The fragmentation of dashboarding tools remains a challenge as well. Many providers lock advanced features behind paywalls, which complicates the vision of a single, vendor-neutral solution. Despite these limitations, the foundation is strong. Experts acknowledge that efficient profiling formats are being explored to handle massive data volumes, which is essential for production environments where every byte of telemetry matters. The primary takeaway for engineers today is that while the public alpha represents a major step forward, it requires careful integration. You cannot simply turn it on and expect a complete replacement for your existing telemetry stack immediately. The timeline for resolving these maturity issues to achieve full parity with established systems is still being defined. The goal is to enable automated performance regression testing and AI-driven root cause analysis. As the standardized data format becomes a prerequisite for advanced observability platforms, the industry will move toward ingesting and analyzing system behavior at scale. This shift represents a transition from static metrics to dynamic, high-resolution execution traces. It captures CPU, memory, and call stacks in production without requiring code changes. Unlike legacy profiling tools that often required sampling or agent-side configuration, the new OpenTelemetry standard enables continuous collection. This means you are not missing data points during high-load periods because the system was too busy to log them. You are getting a complete picture of the execution flow. As we look toward the future of observability, the focus must remain on the correlation of these data points. The ability to link a slow API response to a specific kernel context switch or a memory allocation spike is where the real value lies. It allows us to optimize the data pipeline efficiency in ways that were previously impossible. We can identify when a machine learning model is starving for CPU resources versus when it is blocked by the operating system. This distinction is vital for scaling infrastructure cost effectively. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.